Good evening. Welcome to Lecture 18, Evolution of Low Mass Stars, Part 2. So in our last lecture, we began our quest to understand the evolution of low mass stars, by which, again, we mean stars of 8 solar masses or lower, of which the Sun certainly is one. But it turns out there's quite a bit more to say about that evolution and where those stars are going. So as you all know, I'm perfectly capable of giving a very long-winded introduction before I even get into slide 2. But I'll save that for another lecture. So let's go ahead and dive in. So to remind you where we kind of left off last time, we basically came to the point where a main sequence star has ended its life on the main sequence. The hydrogen in the core is exhausted, so it's all been fused to form helium through the proton-proton chain. And when that happens, the core collapses, right? The radiation pressure vanishes because there are no more nuclear reactions. The core collapses. Eventually, it's stopped by electron degeneracy pressure. When that happens, the surface of the star balloons out. And as that occurs, the star moves up what's known as the red giant branch. Again, not a creative name, but the star turns into a red giant as it moves up this branch. Now, during that process, remember, there's no fusion occurring in the core itself, actually, which is a little bit different than what we're used to, right? During the main sequence stage of a star's lifetime, all of the nuclear fusion is occurring in the core. Well, now that the core is made of helium, even though it has gotten heated up something fierce by that core collapse, it still isn't hot enough to fuse the helium, because helium fusion requires much higher temperatures than does hydrogen fusion, because the electrostatic repulsion between those nuclei is so much larger. So even after the collapse of the core, during the red giant branch, the fusion is not occurring with the helium in the core. Where fusion is occurring is in a relatively thin shell surrounding that core. So, originally you only had the core fusing, but now it collapsed. It generated a lot of heat through that collapse. And as a result, the hydrogen that is now immediately around the much smaller core is in fact hot enough for the proton-proton chain to occur. So that's what's happening as the star walks up, metaphorically of course, walks up the red giant branch. You're just fusing hydrogen to form more helium in this thin shell. That helium then gets dumped into the core and continues to heat that helium up. So as you move up, as a star moves up the red giant branch, you're getting more and more massive helium core, hotter and hotter helium core, and eventually you reach a point at which you finally do get hot enough in that degenerate helium core for helium fusion to occur, where helium particles are going to be combined to form something heavier. And that is an instant known as the helium flash, because it occurs essentially all at once, and essentially the entire degenerate helium core begins burning, in a nuclear sense, begins fusing all at once. And that helium flash is the tipping point, if you will, or where the star moves off the red giant branch and begins on a new branch known as the horizontal branch. And in this branch, again, the core is now fusing. Again, helium is fusing with helium to form carbon in a new process known as the triple alpha process. So as we are accustomed to, if we're going to define we tend to associate branches on the HR diagram with what kind of fusion processes are occurring there. You remember we spent quite a lot of time digging into the details of the fusion reactions that power main sequence stars, those being the proton-proton chain primarily. So now we're going to do the same thing on the horizontal branch and take a look at the specific nuclear reactions that power a star in that stage of stellar life. And again, that's known as the triple alpha process. The reason for the name, which is, again, once I tell you this, will help you remember what those reactions are, is that an alpha particle is just another name for a helium nucleus. And if it seems annoying that scientists would come up with two different names for the same thing, well, it's because they didn't always know they were the same thing, right? It turns out there were three primary types of nuclear of radiation, which were named alpha, beta, and gamma, the first letters of the Greek alphabet. But it was only later that physicists discovered that that alpha particles are in fact helium nuclei. So the name stuck, and so very often a helium nucleus will be known as an alpha particle. And so this triple alpha process, which fuels stars in the horizontal branch, at the highest level, is a process in which three alpha particles are fused together to form a carbon-12 nucleus. And so again, the name kind of says it all. Triple alpha process, you're fusing three alpha particles, and if you start off with three alpha particles, you end up with something with 6 protons and 6 neutrons. And if you just look at your nearest periodic table, you'll see that's going to be a carbon-12 nucleus. Carbon because it has 6 protons, and that defines carbon. Carbon-12 because there are 12 nucleons total, 6 protons and 6 neutrons. But just as was the case in the proton-proton chain, where we said at the highest level we're combining 4 protons to form an alpha particle, it's not quite that simple. There actually are a series of reactions that occur. So let's see a little bit more about that. One thing that I do want to remind you though, and I mentioned this just a couple of minutes ago, is that the temperature for this reaction to occur or for this process to occur is much higher than is the necessary temperature for the proton-proton chain. Remember, for a star, for a protostar to turn into a real star, the defining property is that nuclear fusion has to occur in the core, namely the proton-proton chain. And as we've talked about, that requires temperatures of essentially 12 million Kelvin. Okay. The temperature required for helium fusion is much higher because the electrostatic repulsion between those nuclei is much higher. So what are these reactions? Well, again, in the end, we're going to be combining 3 helium nuclei, 3 alpha particles, but they don't all collide instantaneously. Sometimes, I want to warn you, sometimes people will describe it that way, and I'll talk about 3 things combining instantaneously, all at once, but it never quite works like that, or almost never quite works like that in nature. So in reality, what happens is that first you have 2 helium nuclei, 2 alpha particles collide and form a beryllium-8 nucleus, and that's a bang, and there's some energy released. But it turns out, importantly, beryllium-8 is not very stable, and so just left to itself, it will actually disintegrate or fall apart back into those 2 alpha particles, and that would not be a very efficient way to fuel a star, because you'd get some energy out and then you'd give that energy up. Okay, so in the triple alpha process, what happens is that before that beryllium-8 nucleus can fall apart, it gets hit with yet another alpha particle, right? And if this seems unlikely or improbable, well, it doesn't happen under sort of our everyday conditions, right? But in the core of a red giant star, the densities in that core of helium are gargantuan, right? I mean, there's a whole lot of helium nuclei packed into a very small, relatively small space, certainly on the scale of a star. And so it's dense enough that this will happen. And when that beryllium-8 collides with the 3rd alpha particle, they fuse again, they form a carbon-12 nucleus, and carbon-12 is quite stable. More energy is released, and thus you have the triple alpha process. So good news for you is that this process is actually, it's a couple of steps, but it's only a couple of steps. So if you were having, sort of dreading a revisiting of the several steps of the proton-proton chain, it's simpler here. You combine first 2 alpha particles, then you add a 3rd alpha particle, and you get your carbon-12. In that process, you do release a gamma ray. So remember, gamma rays are the highest energy range of the electromagnetic spectrum. And so some of the energy is carried off in the form of that gamma ray, and then some is carried off in the kinetic energy of the carbon-12 nucleus, which is just a fancy way of saying that carbon-12 nucleus is going pretty quickly. Okay, so it has energy of motion. So let's take a look now. Let's back way up. We just zoomed way in and looked at the nuclear reactions that are fueling this process. But let's back up again and look at the large-scale structure of the star. So there are two main things that are going on in terms of the fueling process of a star on the horizontal branch. So the first thing is what I just described. We've got the triple alpha process occurring in the degenerate helium core, which is converting helium into carbon. But remember, this whole thing was started, the helium flash, which initiated the star's movement to the horizontal branch, was set off by the fusion, by the proton-proton chain that was occurring in the thin shell surrounding the core. And that's still going on. So all the while after the helium flash, when helium is fusing to form carbon in the core, you continue to fuse hydrogen to form helium in the shell around it, which continues to heat up the whole system, right? So we've moved, whereas up until now, we always only had one part of the star that was fusing, whether it was the core on the main sequence or this thin shell on the red giant branch. Now on the horizontal branch, we've got fusion occurring, two different types of fusion occurring in two different regions of the star. Now, as this happens, and I think I've mentioned this in passing before, but I want to emphasize it, at each stage of a star's evolution, essentially the time scale of that evolution gets shorter. So in other words, a star is going to spend some amount of time on the main sequence. Once it moves off the main sequence onto the red giant branch, it's going to spend much less time as a red giant than it did on the main sequence, maybe about 1/10 of the time. So for example, if the sun is going to spend about 10 billion years on the main sequence, it might spend around 1 billion years on the red giant branch. It's going to spend less time again on the horizontal branch. And so with as a star moves into each subsequent stage of its evolution, it takes those steps faster and faster. And so again, just to kind of put some numbers on this, for the sun, which is a pretty typical low mass star, 10 billion years on the main sequence, about 1 billion years on the red giant branch, and only 100 million years, I say only, on the horizontal branch. So again, it's about dividing by 10 with each subsequent stage. And if you pause for a second, you might convince yourself of this, but I'll just tell you, as the masses of the stars get higher, these times all get smaller, right? Because it's quite generally the case that more massive stars are hotter stars, their cores are hotter, the nuclear reactions go faster when it's hotter, and so the fuel is spent more quickly, and each stage moves faster. So these are typical numbers for the sun. Good to keep in mind since the sun is our favorite star, but equally important to know that if you had a 2 solar mass star, all of these numbers would be smaller. If you had a 4 solar mass star, they would be smaller yet, and so on. But again, this describes all low mass stars. So anything less than 8 solar masses, this is what's going to happen. But the specific time scales will be somewhat different. Now, as far as this lecture goes, I have some good news now, which is that while I've been known to belabor the point at many and various times during the course, I'm not going to do that now because we spent quite a lot of time talking about the end of the main sequence stage of a star's life. And as you recall, what precipitates the end is just that all of the fuel is gone, right? The main sequence is defined by fusing hydrogen to form helium in the core, and so when the hydrogen is gone, the main sequence stage of life is gone. Well, the same thing is obviously going to happen here. So in the horizontal branch, we've got a situation where, again, we have two types of fusion going on, helium to carbon through the triple alpha process in the core, and hydrogen to helium through the proton-proton chain in that shell. But again, we're gonna run out of fuel in the core. And so what happens next is the question. What happens when the triple alpha process reaches the end? Okay, well, carbon now, instead of helium, is going to build up in the core. And so instead of having degenerate carbon, or a degenerate helium, now we have degenerate carbon. When there's no more helium to fuse, we have, again, a second core collapse, right? So just like the core collapsed at the end of the first stage of life of the star, it's going to collapse again. It's going to heat up even more, and the surface of the star is going to balloon out even more. And so it's a second version of the same basic process. And because of the additional heating that collapsing core generates, you get a new layer of shell burning begin. And now you restart some helium burning. So I do want to pause here because, I told you I wouldn't belabor the point, but there's a few different things happening here, right? And so I don't want you to get lost. The good news about this being virtual and me recording these is that you can always go back and listen to it again. But what's happening here, right, is that the innermost part of the star, the core itself, which is in gray here, it collapses, and now it's degenerate carbon. Okay, so it's really hot carbon now, but not hot enough to fuse carbon, right? So it's just really hot carbon. But that collapse generates enough heat. Again, you're converting gravitational potential energy into thermal energy or heat. It generates enough heat that now there's a thin layer of helium that's surrounding it that begins to fuse. So the triple alpha process starts up now, not in the core, but in this thin shell around the core. Well, outside that, you have yet another thin shell, which is continuing to fuse hydrogen to form helium through the proton-proton chain. So if you have trouble remembering these details, just remember with each stage of stellar life, you develop another layer, is essentially what's happening. The only question is which layers, whether the core and or one or two layers have fusion processes going on in them, and so that's something to review. So we've got hydrogen burning shell. We have on the outside, with the outside of the core now, right? You've got a helium burning shell inside that, and then a degenerate carbon core, which is really hot, relative to anything else that we've seen so far, but still not hot enough to fuse that carbon. So the degenerate carbon core just sits there being really hot. And again, just like we saw before, the extra energy that's being released in this process as the core collapses causes the outer envelope to expand, and when it expands, it cools. And so it was already a red giant. Now it's becoming bigger and even redder. So the surface is cooling, but it's getting much larger. And so what do we call this? In the spirit of not being creative, we call this thing the asymptotic giant branch. And so this is the phase when both hydrogen and helium shells are fusing, and the star gets big again. And so I think it's useful to come back and look at what we've done so far as movement on the HR diagram. Again, for the sun, you spent 10 billion years sitting here on the main sequence, but after that, you got big, right? As you walked along the red giant branch, you got bigger and bigger, more and more luminous. On the horizontal branch, your luminosity stayed pretty similar, but then you start getting, and you actually contracted a little bit during the horizontal branch, and then and you can see that, by the way, by looking at what's happening on the HR diagram. The temperature is increasing. This is the surface temperature is increasing, but the luminosity is staying very similar. So if the temperature is increasing, the luminosity would also increase unless the star shrinks. So the star is shrinking. It's getting bigger on the red giant branch. It's shrinking on the horizontal branch, but now on the asymptotic giant branch, it again starts to expand. And so the temperature is falling, on the surface, but the luminosity is getting, noticeably larger because the thing is getting much larger. So, as the name kind of suggests, asymptotic, on the asymptotic giant branch, stars get really, really huge. So huge, in fact, that the gravitational force remember, it's gravity that's holding the star together. The gravitational force on the surface is so weak that it's actually easy for material on the surface of the star to escape through solar flares, radiation pressure, just more or less chaotic motions of the very hot plasma that's out there. It's easy for those particles to escape. And schematically, you can kind of look at this picture that we've come back to of the equilibrium of a star, where you have the gravitational force tending to collapse the star, and some internal pressure, whether it's radiation or electron degeneracy or whatever it is, balancing out that force. Well, we've seen what happens when the internal force vanishes, right? When the internal pressure vanishes, then the star collapses. Well, in this case, you have a situation where essentially, at least to some hand waving approximation, the gravitational force almost, essentially vanishes on the surface. And so now you still have some internal pressure, but gravity is extremely weak. And what happens then is the formation of nebula, of planetary nebula. And don't let the name mislead you. Unfortunately, this is a case where the name is not very creative, but it's also not very accurate. So planetary nebula were named that because way back in the day, when these sort of fuzzy objects were first seen in the sky, I guess maybe somebody thought, well, that looks kind of like a planet or something. Turns out we know what they are now, and they're not planets. What they are is this escaping layer, escaping layer of the star that just gets lost out into interstellar space and just moves off and keeps moving because it overcomes the gravitational force, which again is very weak out where it is. And it turns out that this can be the planetary nebula can be quite a large fraction of the total star's mass, up to roughly half. So at the end of life, a star can lose up to half of its mass or thereabouts in the form of a planetary nebula. And the good news for us is that they can make some extraordinary pictures, some of which I think I've shown you already, and there are plenty more that still wait to be seen. And you didn't have to wait very long for me to fulfill my promise, because here are a number of more sort of flagrant eye candy planetary nebulas. We've seen some of these before, but they're always worth putting up again because these really are some of the prettiest pictures that you get in astronomy. And astronomy is known for producing pretty pictures. So feel free to mute me and just pause and look at these, to your heart's content. And here's a particular one. The names that I harp on the fact that we're not creative in physics and astronomy with naming schemes, but there are some pretty creative planetary nebula names, some of which are more obvious to me than others. This is the Eskimo Nebula. I confess, when I look at this, I don't see anything that resembles an Eskimo, but maybe you do. And here are some more pictures taken of the Helix Nebula, also known as NGC 7293. It's the same nebula, but taken in different bands of the spectrum. And so upper left-hand corner is sort of, you filter out everything but the hydrogen alpha line. So you're looking specifically at a wavelength of 656.3 nanometers. And then similarly, you look at the oxygen 3 line, helium 2, and so we've seen these kinds of things before, some lectures back when we looked at the distribution of gases of different kinds like hydrogen, carbon dioxide or carbon monoxide, and so on in the Milky Way. It just gives you an idea about where the different elements are that are making up the planetary nebula. And this one should look familiar to me. This is one of my personal favorites. It's the Cat's Eye Nebula. This is one that I do look at and I say, yeah, I can see why you would call it that. And I liked it well enough to make it the cover picture for this series of lectures. So if it doesn't look familiar to you, that's a bad sign. Go back to slide 1 and take a look. And this is just gratuitous eye candy. 25 planetary nebulas all at once. So as I said, there are lots and lots of these things out here. They're sort of, phenomenal to look at in my mind. And so, if you start to get depressed or that you feel like this class is too much work, come back to this and hopefully it'll make you feel better. So, and this is, I'm not going to spend a lot of time on this slide, but this is a nice sort of summary slide that just kind of sort of recaptures or reiterates everything that we've kind of studied over the last couple of lectures, where you start off with a main sequence star on the star on the main sequence, and then you go through the the evolutionary stages. And so we've done the vast majority of this, right? We've started on the main sequence. In fact, we even started before that as a protostar. Talked about the Hayashi track as the star sort of through gravitational influence collapses and eventually begins the proton-proton chain. But you go through the various stages of using up the fuel in the core collapses, the surface balloons out, you start more fusion, and more fusion. Eventually you leave the red giant branch at the point of the helium flash, enter the horizontal branch. You finish that stage, you start the asymptotic giant branch, and then we finally come to the place where you eject a large fraction of the star's mass in the form of a planetary nebula. And we've said that, but we still have to say something about, well, what's left behind? Because I made the claim that you can eject up to half of the mass of the star in the form of a planetary nebula that just basically floats off into space, giving nice pictures. But what about the other half of the star's mass that's left behind? And at the risk of playing spoiler, you can kind of see where we're headed. And that's something that you may or may not have heard of, which is known as a white dwarf. And so if you look at the HR diagram now, we've spent all of our time here so far, basically in this part, and it's kind of a compressed part. So the asymptotic giant branch is really, it's kind of up at a pretty sharp angle here. But we've talked a lot about this, and then the process of planetary nebula ejection is a pretty long one as far as the track, in the HR diagram is concerned. But these are the post-asymptotic giant branch stars. As the luminosity falls, eventually you get over here, and the planetary nebula is lost. But what's left behind is a very dense, much smaller mass now, lower luminosity, white dwarf. And so that's what we're going to spend a few slides now talking about, is what do we know about and what are the characteristics of these white dwarfs that are left behind. And this is just before we actually say a lot of detail about white dwarfs. Here's just another rendition of that of the previous slide with a little bit more detail, because I know a common complaint about this class is I don't give you enough details, I don't give you enough information to learn. That was a joke that usually gets more chuckles or more wide eyes when the class is given in person. But here it gives you some numbers, to give you a sense of how long are each of these stages, and so on. And for good measure, we'll put the Hayashi track on there by hand. Okay, so what can I tell you about these white dwarfs? So a white dwarf is what's left behind when a low mass star reaches the end of its life. It's a degenerate carbon and oxygen core. We've talked a lot about the carbon specifically, which is formed through the triple alpha process. The oxygen is produced by other nuclear reactions that we have not focused on. I did mention earlier in the course when we first started talking about the proton-proton chain, that there were a number of different nuclear reactions that do take place in these stars. We have not talked about all of them, and we won't, for which you're welcome. We talk about the dominant reactions, but there are other reactions that occur as well to a lesser degree. And one of the upshots of that is that there actually is some oxygen that is produced in these stellar cores as well. So a white dwarf is this collection, very dense collection of degenerate carbon and oxygen. And they are, first of all, extremely hot. So surface temperatures of around 100,000 Kelvin when they first form. That's why they're white, so white hot, because they're hot enough that they're producing very similar. Well, I mean, obviously not all wavelengths are produced at exactly the same level, but they're producing all wavelengths in the visible spectrum to a sufficiently similar degree that we perceive them as white. As it turns out, these things are not. These things are quite common, actually, right? Because I mentioned sometime back, 97% of stars in the universe are low mass stars, and all of those low mass stars will end their life as a white dwarf. Okay, so there are a lot of them. There are a lot of them out there. The brightest star in the sky, as viewed from Earth, whose name happens to be Sirius, is actually a binary star system. So another case where he got named Sirius because it just looked like one dot, but then our telescopes got better, our resolution got better, and we found, it's actually two things. And so it happens to consist of an A-type main sequence star that has a white dwarf binary star, which are now known as Sirius A and Sirius B, respectively. So I want you to think for a second about the following question. If Sirius A and B were both formed at the same time from the same cloud of gas, which star was more massive when the stars formed? So I'll do my usual pause for 30 seconds or so. You're welcome to pause it for longer before I spoil it, and then I'll come back and I'll tell you what I think. Okay, well, I'm going to spoil the surprise, and so feel free to pause me if you're not quite ready for it. But the key is to recognize that if these stars were both formed at the same time, which is a really darn good bet, because in general, binary stars form at the same time. So if they're formed at the same time, and one of them is a white dwarf and one of them is not, that means that the white dwarf lived a shorter life. It progressed through the stages of life more quickly, right? Because it's reached the end of its life as a white dwarf, whereas Sirius A continues to fuse as a real star. And so the result is that Sirius B, the one that is the white dwarf, must have been more massive when it formed. So I told you that these white dwarfs are hot, which is why they're white, but it turns out they're also really small, at least small on the scale of stars, very similar to the size of the Earth, in fact, but with, again, half or about half of the mass of the sun. This is for a solar mass, a white dwarf. So starts off with the mass of the sun, loses about half of its mass in the form of a planetary nebula. The other half of its mass is still there, but now this the degenerate carbon-oxygen core has shrunk down to the size of the Earth. So remember, the sun started out as roughly 1,000,000 times larger in volume than the Earth. And now you've taken half of that mass and squashed it down into the size of the Earth. And if you do the math, what that means is that the density has gone up by about a factor of 500,000. So this is a really dense material, much denser than anything that we have on Earth by orders of magnitude. And so if you do the math a little bit more precisely, you find out that no, it's about 200,000 times more dense than the Earth. is. So if you compare the density of a white dwarf to the density of Earth, and just to put that in perspective, if you take a standard dye size of white dwarf matter, it would weigh over 5,000 pounds on the surface of the Earth. So this would you wouldn't be able to hold it. And finally, these things are inert, it turns out, by which, basically, I mean, they're not doing anything. They're just sitting there being really, really hot, and cooling down because they give off thermal radiation. Again, anything at non-zero absolute temperature gives off black body radiation, right? So they're white because they're giving off very intense, very high energy black body radiation. But over time, because they're giving off that energy and there's no internal energy source anymore, they will cool down. So, they're really hot, but they're not hot enough to fuse what's left. So they have carbon and oxygen left. Those nuclei have 6 and 8 protons in them respectively, 6 protons for carbon, 8 protons for oxygen. They repel each other even more strongly than did the hydrogen or the helium, right? And so there is a temperature at which you could get those to fuse, but these low mass stars will never get there. And so the white dwarf just sits there alone in space, or maybe it has a binary partner, gives off that thermal black body radiation, over time will cool down and will eventually disappear. It'll eventually stop being white, it'll become kind of yellowish, then reddish eventually, and then eventually will be emitting in the infrared and will vanish from sight. So it's kind of a quiet end to a life cycle, but that's how 97% of stars in the universe, these low mass stars, will end up. So as it turns out, there is still quite a bit more to say about evolution, stellar evolution. And in particular, the evolution of binary stars, in which there can be an interesting wrinkle or two, or modification to stellar evolution by virtue of there being a binary star partner. So, but I've decided rather than include that here in this lecture, I'll break that off into a separate, smaller lecture. So hopefully you'll come back for that one. So I'll just wrap up this lecture by coming back to our favorite diagram, the HR diagram, and reminding you of a couple of things that I've said before, what I think is good to keep in mind as we prepare to finish up our discussion next lecture on the evolution of low mass stars, and then get ready for evolution of high mass stars, which will be even more exciting if that's possible. But as a reminder, we can divide stars on the main sequence into these two basic classes, right? High mass stars, which we have not really talked about yet, at least not in terms of evolution, that live up in the upper left-hand corner of the HR diagram. Very hot surface temperatures, and of course even much hotter core temperatures, and very luminous. And because of those hot surface temperatures, they appear bluish because that's the high energy part of the spectrum. Those high mass stars are by definition greater than 8 solar masses, right? And the reason is, as I mentioned a few lectures ago, just because it turns out that that's the dividing line that kind of distinguishes between two different types of stellar evolution. So stars that are low mass stars, less than 8 solar masses, evolve in one way, and stars that are high mass stars, or greater than 8 solar masses, evolve in another way. So we've talked about these low mass stars, so now you know how 97% of stars in the universe evolve, but there is still an important 3% out there that we would like to understand. Not just because in principle we'd like to understand everything, but because there's actually some pretty exciting differences with these high mass stars that by virtue of their higher masses, they're able to give rise to some phenomena that are more energetic and more exciting than what we see with the low mass stars. So hopefully that's enough of a tease to get you to come back for the next lecture. But for now, thanks for sticking around. Thanks for making it to the end of lecture 18, and I'll hope to see you back for lecture 19.